Good morning, students. Today we have to see some problems on design of field winding of synchronous machine. Last section we have discussed respective theory. The theory is also asked in number of times in VT exam. Otherwise, one problem will come. Problem number 1. The field coils of a salient pole type alternator are wound with a single layer winding of bare copper strip 30 mm deep with separating insulation 0.15 mm thick. Determine a suitable winding length, number of turns and thickness of conductors to develop an MMF 12,000 angstrom with a potential difference of 5 volts per coil with a loss of 1200 watts per meter square of total coil surface. The mean length is 1.2 meter. The resistivity of copper is 0.021 ohms per meter and millimeter square. So you have to write down the given details one side. As per step 9 steps we have discussed. As per step you can go one by one. So number 1, area of field conductor equal to ampere turns full load, resistivity, LMT, voltage across field coil. You substitute all the datas, you are going to get 60.4 millimeter square. Then next you can go for height of conductor. Once you are knowing the area of conductor should be equal to height of conductor into depth of conductor. Then you are knowing to height of conductor, again modified value of area of conductor, it is around 60 millimeter square. Total loss dissipating surface, yes, it is given by 2 times of LMT into bracket HF plus DF. You substitute the value, HF keep as it is, can go to the equation. Total loss dissipated, that should be equal to 1200 into this S equation. You frame the expression. Next you can go for calculation of field current. Field current equal to QF divided by EF. So we have to frame one expression. Field MMF, that should be equal to multiplication of current and number of turns. You frame the equation 1. Then 576 HF into TF plus 17.3 TF equal to 12,000. Height occupied by the each conductor, that is given, height occupied by the each conductor 2 plus 0.15, 2.15 meter. Height of the field winding, that is number of turns in the field winding, then space occupied by the one winding, then you are getting the total height. Substituting HF value in equation 1, then you can equate, we are going to get TF equal to 91. Height of the field winding, by using this relation we are going to get around 196 mm. This one problem may give 10 marks. You practice as per the 9 steps, one by one you practice. Problem number 2, a 3-phase 1000 kVA 3300 volts 250 rpm 50 Hz star connected alternator has the following open circuit and short circuit characteristics. Using the synchronous reactance method, find the field MMF full load, 0.8 power factor lagging with the following details. In this problem NS is given, NS equal to 250 rpm. By using this relation, it is possible to design number of poles. It is possible to design number of poles. We are going to get around 24. Now, given that in this problem line voltage is given 3300 volts, hence you determine phase voltage. Phase voltage equal to EL by root 3. The short circuit characteristics is a straight line. Already we are knowing by plotting the OCC and SCC. In usually short circuit characteristics lies a straight line. Short circuit current corresponding to rated voltage from the above table, data is given in the above table. It is possible to calculate short circuit current at rated voltage. That you take the ratio 1910960 into 232. So we are getting around 462 amperes. Once you are knowing the short circuit current, once you are knowing the rated voltage, then you can determine synchronous reactance. Xs equal to P by ISC. Both are rated voltage, both are rated quantities, 4.13 ohms. Then after that you determine rated current as per the knowing of kVA rating of machine and primary voltage. You can determine rated value of full load current. Substituting Q and EP value, we are going to get around 175 ampere. Per unit synchronous reactance, per unit synchronous reactance, I into Xs divided by phi phase, that you are going to get around 0.378. Per unit no load voltage corresponding to excitation at full load and 0.8 power factor. So E naught equal to 1 plus 0.8 plus j 0.37, approximately E naught equal to 1.23. Hence no load voltage 1.23 into 1910, we are going to get this value as 2350 volts. After determining the no load voltage, the field MMF corresponding to voltage of 2350 volts, that is around 8500 ampere. After knowing this field MMF required at full load, then ATFL equal to 8500, voltage across each field coil, that is also given 110 divided by 24, voltage divided by number of poles, we are going to get around 4.58. Then area of field conductor, by using the relation ATFL resistivity into LMT divided by EF. It is given, formula is there, you remember the step. Then height of each conductor, again we are knowing the area of field conductor should be equal to height of field conductor into depth of field conductor. By using that relation, you can go for that. Suppose there are TF turns in each field coil, field current is IF, the height of the field winding is HF. Space occupied by the each along the height, that means one turn, how much space is taken, that is bare conductor with insulation. Insulation is given 0.25, 1.54 plus 0.25, you are getting 1.79 mm. So number of turns TF, so that you are knowing total height of the field winding divided by number of space or height taken by one turn, So we are going to get that value, equation 1. Then amount of heat dissipated, that should be equal to S into loss in watts per meter square of total coil surface, that you develop the equation. By knowing the field current, You calculate the field current IF equal to heat dissipated divided by EF, voltage across the coil. You frame the equation 2. From equation 192, that relation, you have to substitute previous equations 192, then you have to solve. We are going to get height of the field winding is 97 mm. Only these two problems are available in Sahani book. These two problems are repeated. These are very important for second part of the module. We are having 2 questions in each module. Second part consists these 3: design of field winding problems, design of field winding theory, then selection of armature slots. These are all VTU question paper important points. Practice all 3. Thank you.